So, remind you again of the curl, and so it has the three components, and in particular, that means curl F dot K. The K is the K component of the curl. So from that we get in scalar form for the K component partial of n with x minus partial of m with y. So from that, and this is going back to where we were last Friday. We look at the vector form of the Green's theorems in the plane. They'll tell us that curl F for the field is 0 if and only if there is a scalar function either of two variables or of three, depending on whether you're in the plane or in 3 dimensions, called the potential, such that the field is the gradient of this scalar function. And we mentioned last Friday, I think, that we have the vector identity, which is in the back of the book. And if you think of the big sheet of paper that I gave out last week, the appendix where I copied that in the back of the book has that identity printed on that sheet of paper, that curl of a gradient is always 0. So then we have the Green's theorems, which in particular is section 16.4 tomorrow, but I presented them last week, and we're actually using the flux, the circulation curl Green's theorem in the work that we're doing today. So I thought I'd put it in context this way. So we have the flux divergence Green's theorem, as some people would call it anyway. People also call this the normal form of Green's theorem because this is the unit outward. Well, it isn't necessarily a unit vector, but it's the outward pointing normal vector. And so you have then that the integral on the closed path of the outward component of the field is, and if you write it as n with the hat on it, that's a unit vector. And so this could also be written this way, where this, you see, would be the field if you're in the plane as a 2-component vector. And then if you dot this out, you have m dy minus n dx. And Gauss called this a flux integral. And then in any case, that is equal. These are 3 expressions for the same thing. This integral around the contour of the field dotted with the outward pointing normal. You can either write it like this, or write the components of your field, and then the n ds would be the dy minus dx, or then you can do your dot product and say this. This then would be the scalar form of it. In any case, that's equal to the divergence of the field integrated over the region that this curve encloses. And in the book, what in the section 16.4 tomorrow, you actually see the Green's theorem, the normal form of the Green's theorem, like this. This one equals this one, which you see is a scalar form, but it also can be written in terms of vectors, like saying this one equals this one over here. Then the other Green's theorem is the circulation curl Green's theorem, also called the tangential form. And Stokes, if you were here last week, you got the WikiLeaks, which are not all FBI stuff. You see, there was the WikiLeak on the biography of Stokes. And Stokes called this a circulation. Okay, so that's the circulation in circulation curl, and you see the curl is over here. And so the circulation around the closed path, there ought to be a C there. Which is your line integral f dot dr or f dot t ds. The t here would be your unit tangent vector, is curl of the field, and if you're working in the plane so that it's two component, what you have is the curl dot k. The general form is curl f dot the normal, if you're allowing for three component vectors and working in space. That comes later in the chapter. So curl f dot k, and the first thing I was reminding you about this morning is that if you write out the curl, you have this three component vector, so curl f dot k is this part, which you see is right here. So where my right hand is tapping the board matches where my stick is tapping the board. And again, you have a scalar form of this. If you took the circulation integral and said it's this one, that would be scalar to scalar, and that's what you see tomorrow or section 16.4 whenever you look at it. And you can also see that it has a vector form, which would be either one of these equal to this. So in particular, if you're looking at this one, if you have the line integral around the closed curve equal to the curl, then curl f is 0, so that this integral is 0, is equivalent to, which is if and only if, one of the other ways you write this integral is 0. These two integrals are the same thing. So that means then that what we get for the value of our line integral on the closed curve, when it's the tangential component, is independent of path if and only if the curl of the field is 0. Because when the curl would be 0, the line integral would be 0, and that would mean that if you're going from one point around a curve to another, it wouldn't matter how you get there, exactly what the path is. You have then what is the basis of the section 16.3, today's class, and you call that line integral a point function in the sense that the values depend on the beginning point and the end point, but not on the path. So our definition of conservative is that the field is conservative when there is a scalar function of either 2 or 3 variables, depending on whether you're in the plane or in space, such that your field is a gradient. And work done then is independent of path, and that was the example that I presented last Friday. If you remember, I was picking up the book and doing work against the Earth's gravitational field, which is conservative. I let the book go, and the work done one way is a number, force times distance, of course, and the opposite direction, you get the same number with a minus. So if you total it all up, you get 0 around your closed path. And it doesn't matter if I pick the book up straight and drop it straight, or if I pick it up and walk around the room and talk and whatever, and drop it back in the same place, the work is 0. Because it's so much up and so much down, and wandering around in a daze doesn't count, you see. Okay. So then to recover the potential, the scalar function f from the gradient, is what today's class is really about. So first of all, check that the curl of your field now is this gradient. If you do have a potential, check that it is 0 where your field is the gradient. If the curl is 0, there is a gradient to get, and I'm in the process of showing you how to do it. And if the curl is not 0, there is no gradient there to get, and so then you just go on. Then, for example, 16.3 problem 7, we start with this field. If you took curl of this, you'd find that it is 0. The first 6 problems in the homework that are in the book are giving you fields such as this and asking you to decide whether or not they're conservative. In other words, take the curl. Curl is 0. Yes, you call it conservative. Yes, there is a little f function to get. Curl not 0, the answer is no, and you go on to the next one. Take a look now at the maple for the one. Okay. So you see, if you look at the maple, a single sheet of paper, problem 1. So I enter the field, and I call it F, so I can refer to F. And then you can type potential, then what you defined is your field, and you have to say that you're working with Cartesian coordinates. And then if you also type small letter f and put it in quotes, and then it flows your command and so on. If there is a potential, the maple system will say true, which means it tested that curl is 0. And if you have typed the command with the F there, small letter f, then if you type in F, it'll tell you what it is, X, Y, Z. So that means that what you started with in problem 1 is the gradient of X, Y, Z, which of course you could work out and see that F is what you get. And you can ask Maple to do it for you. That's my next command, grad, and then what I called little letter F, which is line 3, and then I am saying Cartesian form. And you see 4 is the same thing as 1. So then I've typed what I've been saying, that line integrals are independent of path. When there is a potential, and the value of a definite integral is the difference then of values from between the beginning point and the end point. If you aren't going around a closed path, but are just on a path from point capital letter A to point capital letter B. So if you use the vector calculus package instead of the lin-alg package, then you, for instance, could type something like for problem 6. So I use F vector field, and then problem 6, you'd see it's e to the x cosine y, and so on. So back comes your vector. Then scalar potential, that would be the function that f in line 6 is the gradient of. And in the same way, if I check my work by asking for the gradient of what was line 7, remember when you use the percent sign, it means with a command, whatever the command is, parentheses percent sign means apply that command to the previous line, most recently executed. So it means gradient of the formula in line 7, and so that gives you line 8, which is, you see, the same as line 6. And then I've done that same sort of thing with problem 3, and you see what you get back with problem 3, your field is line 9, and I ask for the scalar potential of line 9, and it doesn't give me an answer, it just gives back what I typed. So it gives you no response, not even an error message. So that tells you that the thing is not conservative and there is no scalar potential for it. And it also would be equivalent to telling you that the curl is not 0. If you took the curl of problem 3, then you would find that you don't have 0 as your answer. So that's how you do things with Maple. So now let's look at doing problem 7. From 7 through 10, they're telling you to get the scalar potential. So basically they're promising you that there is one to get. You can take the curl if you want to, but the curl will reliably be 0, so I don't bother to write it on the board. But look at problem 7. So here you want the small letter f, the scalar potential that this thing is the gradient of. So that if it's a gradient, then the first component is the partial with x. The second component is the partial with y. The third component is the partial with z. So you have to dream up something involving x, y's, and z's that'll give you this for partial with x, this for partial with y, this for partial with z. So you take, there isn't any law that says you have to take things in order left to right, but I think it's the natural thing for all of us to do because we read that way. So 2x then is your partial with x. What is this function? Well, integrate both sides. So then your f would be your integral with x of your partial with respect to x, and it would therefore be the integral of whatever that equals, which is here. But instead of writing plus constant, it's more than just constant because it is any function, so it's the most general function then, for which the partial with x would be 0. So that as long as it's a function involving only y's and z's, the partial would be 0. So this little letter g of y and z could be theoretically just a constant, but it could also be y, sine y, cosine z, or something like that, because the partial with respect to x of, for example, sine of y, cosine of z, would be 0. So what I get here is then that my scalar potential has the form, it must have an x square so that you get this for its partial with x, and it can involve some y's and some z's. So I wrote it that way, okay? So then that's continued over here. Now go to the next component, 3y, which has to be your partial with respect to y. So it's partial with respect to y of all of this. So you have x squared plus this function that involves y and z. So it's out of this g of y and z that you're going to get what you need that'll give you 3y when you differentiate. So that says that the if you take the partial with y of x squared, of course you get 0. So you get partial of g with respect to y out of here, and that has to match your second component, your 3y. So then what you know is that if you want to solve for g, that g, if you integrate this side, would be the integral of this, 3y dy. And again, instead of saying plus constant, it could be just a constant, but it could also be any function of z only. So you want the most general function where its partial with y would be 0. So you would get 3y squared over 2 from here, and then the unknown function h of z. And now you have to determine that. Same game. So what you know at this point is that your scalar potential is x squared plus the g, and the g in turn is this, 3/2 y squared plus h of z. So you could check your work at this point. Partial of this with x is 2x. Partial of this with y is 2 canceling, leaving you 3y, because the partial of a function of z only with respect to y is 0. So this thing works there and there. Now you have to make it do this. So your derivative of the function of z only you can write with partial symbols, but actually it's only one variable, so you can also use your prime mark if you want, or straight up and down letters D if you want. And so that's for Z. So h of z is the integral of the h prime. So it's the integral of 4z, which is 2z squared. And now you can write plus any constant that you want. So what I'm saying is that my scalar potential then is x squared from there, 3/2 y squared from there, and h of z, which now is 2z squared plus constant. And if you check your work for any constant, the gradient of this, see, gives you 2x there, 2's canceling, 3y there, 2 times 2 is 4z there. And if you wanted to take curl of this thing, you'd find that it is 0. Okay, so this is an example of how you do it to recover the potential function from its gradient. This is also a technique you use in differential equations, the Math 333, to solve a type of differential equation that's called an exact differential equation. So it's worth remembering how to do this for that class also. So what this means, among other things, for a field like this that is the gradient of a potential, is that, coming back to here, if you're doing a circulation type line integral, whether you think of it this way or that way, then if it's not a closed path, but from one point, and if it's 3 variables, coordinates A, B, C, to an end point, coordinates H, K, L, then it'll be the potential evaluated at the end point minus evaluated at the beginning point. So, like that. The way that you write things when you do definite integrals, you get your antiderivative and you have the vertical line and you have the starting point at the bottom and the ending point at the top. It's just the same idea as Math 170, except there's more variables there. So if the problem gave you these coordinates and those and said, what's the line integral, then you wouldn't have to parameterize your field and whatever your curve is. You could simply, in this case, find the potential and then take the difference in values. So this is a fundamental theorem of calculus for line integrals. You have one when you have the kind of field where it is a gradient, or where its curl is 0. So we call a field of this type, where curl is 0, and the line integral depends on the difference of values of the potential, a point function, because the value depends on the difference at the 2 endpoints in values of the potential function, and is independent of the actual curve. So if you have something where curl is 0, you can, and you want a line integral from a point, say you call this So you call this beginning point capital letter A and this end point capital letter B. If you have a setup like that, you can either get the potential, as I'm saying, and take the difference, which is probably what you do, or if you wanted to, you could, if you didn't like the path you were given, to parameterize using that path, you could substitute a different path, since it's independent of path, and parameterize some other path of your choosing. Say if it were some curve that was awkward to parameterize, you could replace your path with the straight line from A to B, because a straight line is always reasonable to parameterize. It's chapter 12, the straight line from point A to point B. So you could always do that. So there are a lot of different choices that you have. As I have said already in words, the point function idea is the fundamental theorem of calculus for line integrals. The thing is that it applies if and only if your field is the type where its curl is 0. So it doesn't apply for every problem. But this is a particularly important situation in thermodynamics, because if you're in engineering, you either are taking thermal, have taken it, or will, and if you do, you'll see that there are kinds of line integrals you do there that are this point function type where the curl is 0. Well, let's go to the other end here. At problem 10. So it wants us to recover the potential from its gradient. It's the same idea as what we did, except that it has some trig functions in it. So once again then, you want the partial with x to give you y sine z. So I'd start there. As I said, there isn't any actual law that says you couldn't first start with partial with respect to y is supposed to be this, or you could start with partial with z is supposed to be this. You could work backwards. But you have 3 choices, so you have actually 3 factorial ways you could do it. There's 6 different schemes you could follow, but I think going left to right is what a sensible person would do. Not that I'm always sensible, but once in a while. Anyway, say that this is your partial with x, then if you're integrating both sides, your scalar potential is this integral with respect to x, and again, in place of writing plus constant, anything that would disappear when you took its partial with x would apply here. So the most general answer would be a function of y and z only, but not of x. So here you're doing your partial integration. You notice there's no x there, so all you're doing is multiplying by x. So now your scalar potential has to look like this. So then the center term of your field is the partial of f with y, so it's the partial of this with y. And so if you do the partial here of what I have, which I've indicated, that says that your center component, x sine z, is what you get out of here when you do the partial with y. Notice there is a y there, so when you take your partial, it leaves you the x sine z, and then partial with y of the g. Now notice that there is something here with an x in it, and there is also something over here with an x in it. And as it happens, the somethings cancel. If there's going to be a potential, in other words, that's if and only if curl here of this is 0, then this that you see is what always happens, that on the left and on the right, the terms that do involve x cancel out, because if g is to be a function of y and z only, its partial with y cannot involve any term with an x in it. Because if it has an x in it, it's not a function of y and z only, there's x's there. So if your quest, if you want that word, to get a scalar potential is going to succeed, then in the steps like this, where you have some letters x from the first time around, when you're looking for the function of y and z only, the terms with a letter x have to cancel. If they fail to, then you have a field where the curl wouldn't be 0 and where there is no scalar potential. It isn't that you're doing something wrong, it's that you're after something that just isn't there. Okay? Kind of like an honest politician. You're after something that just isn't. Admit it and go on. Okay, anyway, couldn't resist that. The key concept here is that your partial with y must not include x. If the terms that include x fail to cancel, as here they do cancel, there will be no potential and curl f will not be 0. So with our partial of g with respect to y being 0, see, these cancel out, but leaves you partial of g with y is 0, then the g is actually a function of z only, possibly just a constant. And so you can write what we got at this point. You can rewrite that down here. F of x, y, z equals x, y sine z. And instead of g of y and z, it's just function h of z, which in turn may end up just being constant. It may end up that this is our potential right here. Okay, so then finally, third component has to be the partial of all this line with z. So it'll be x, y, derivative of sine here, which is cosine, and the partial of h with z is actually h prime, straight up and down d's, because it's one variable only. So our partial with z, first of all, from what we're given, goes on the left side. So this right here is how I get that. And then on the right side, I do partial with z, and you see I get xy cosine z, and then I get h prime. And again, the terms that include letters other than z have to cancel out to have something that equals the derivative of a function of z only. And you see they do. So h prime of z is actually 0, so it's a constant. And this is our scalar potential. And you could check that the gradient of this thing takes you back to here. And that's easy to do. Partial of this with x is the y sine. Partial with y is the x sine. Partial with z is xy cosine. So that means if you were doing a line integral from point A to point B on any path whatsoever of this field dot dr, you could simply say it's the value of this potential function at point B minus the value at point A. You don't really have to parameterize at all. Or if you wanted to, and you didn't like the path C that you were given, you could change to a straight line path and parameterize that and do it like we were doing parameterized integrals last week. So we call a differential exact. This is where the connection comes in with differential equations, really. When there is a potential, in this sense, that your differential is the gradient of this potential function dot dr. So it's partial with respect to x dx plus partial with respect to y dy plus partial with respect to z dz of this field, or pardon me, not this field, but this potential, as we're calling it. So the dr would, of course, be like this. This is the same thing we had in chapter 14 when we were starting the section with the chain rule, section 14.3, I think it is, where we had at that point a curve traced out by the tip of a vector r of t, and then the dr was the gradient dotted with, well, the curve was f, let's say, equals a constant on a surface, and that's traced out by the vector r of t, and so the df was the gradient of f dot dr. So here again, if you have an integrand that's exact, then the line integral of df, which is the f dot dr, is this difference in values, this fundamental theorem of calculus idea. The scalar potential at B minus scalar potential at A. So take a look at problem 14. So it wants the scalar potential for a df that looks like this, which is gradient dot dr, where the dr gives you the dx, dy, and dz. So yz is your partial with x. So your f of your scalar potential is the integral of yz with x, again, plus anything that does not involve x, so that its partial with x would be 0. So that'll get you x, y, z plus this. Then take the partial with y, which will get you the xc on the left, and it will you'll get the xc on the left from the coefficient here of dy in the center term. So this XC is that one, and then when I do the partial with Y, the XC here is this one, and then partial of G with Y. So like problem 10, the terms with X's disappear, and my partial of G with Y is 0, so my function of Y and Z is a function of Z only, and maybe just a constant. And the potential I'm trying to get has the form x, y, z plus h of z. Then, third time, the xy here is your partial of this with z, which is xy there plus h prime, and those cancel. So h prime is 0 and h is constant. So my scalar potential is xyz plus any constant. So then if I want the line integral from 112 to 350 of this f dot dr type integrand, which you notice is what we call exact because it can be written as the differential using a scalar potential like this. In other words, it's the differential of x, y, z equals constant. Then you can take the value at this point minus the value at that point. So because you have a 0 here for your z, and you're taking values of x, y, z, of course you're multiplying by 0. So at the upper limit your value is 0. At the lower limit you're putting 112 into x, y, z, and so you have x equals 1, y equals 1, z equals 2. So then minus 2 is your answer. And that's what the book has. Notice your maple. I have problem 13 at the bottom of the front page. And the field you see is 2x, 2y, 2z. It has a scalar potential, which is line 11. And I then did the same thing with the vector calculus. And then if you want the difference in values of the scalar potential, use sub for substitute. And x is 2, y is 3, z is minus 6. In the g of x, y, z, you get 49. And then at 0, of course, you get 0. So the value, the integral, is the difference. This is problem 13. That's a different problem than that one, but this is the same concept with a different problem. So when we take a look at, well, I guess this one was problem 14. So then the last thing here, if you look at problem 26, it wants us to show the value of the integral a to b f dot dr is independent of path, where the f is like this. Notice that my r dot r is the same thing as, if you think of r as x, y, z, then r dot r is x squared plus y squared plus z squared. So it's the same as if these denominators are square root of x squared plus y squared plus z squared. If you want to show that it's independent of path, then one way to go about it is to find a potential that you have the gradient of. So it turns out that this would be your potential. You can see that because if you think of this as the half power, then when you do your gradient, you have partial of this one with respect to x. So if this is half power, you have 1/2, your expression to the minus half, times by the partial derivative of the inside function with x, which would be 2x. And then the 2's would cancel. In the same way, your partial with y would be 1/2, this to the minus half, 2y, and the 2's would cancel. And the third time out, you'd have this same expression minus half times z. So what this first one will give you is x over the square root. This one gives you y over the square root, and this one gives you z over the square root. And you see that's what this is. The r dot r is this sum of squares. So I've demonstrated that it's independent of path by demonstrating a function that will serve as a potential. The other way that you could do it, of course, is you could take the curl of this, and the curl of gradient is supposed to be 0. So if this thing is a gradient, instead of producing the potential and demonstrating that the appropriate partials that make it a gradient of this give you what you started with, you could do curl of this thing. So if you were trying to do that, what you will end up with is like this. The curl of this will give you the common factor 1 over the sum of these squares to the 3/2, and then the vector part, you'll have yz, xc, xy minus exactly the same thing. So of course you get 0. So just for example, how I'm getting these 6 entries here, remember each of these entries is the component here, any of these 6, over this common denominator, which is the sum of squares to the 3/2. So just to see how that works, I don't have space to write the whole thing, obviously. If you're doing your curl, you're doing I, J, K, your cross product, your partials, and then these things, x over the sum of squares, y over the square root of the sum of squares, z over square root of the sum of squares. So this is square root of the sum of the squares. So look at, for example, this one, where I have the an I component partial with y and then z over the square root. You notice that in each of these 6 products, where you have a partial with one letter and you have a numerator here that's a different letter. So this would be partial of z with y, this would be partial of x with z, this one would be partial of y with x, coming back, partial of y with x, partial with z of y, and partial of x with z. So that means if you're looking at one of these, partial with x, I guess it's this k one here, the y, and then what would be under the square root sign, I wrote the sum of squares with the minus half power. You'd expect a product rule, but one of the factors is 0, because it's partial of y with x. And that kind of thing is true in all 6 cases. So you really only have the y and then the partial with x of the factor that has the minus half power. And all of those act the same way. They're minus a half, your sum of squares to the minus 3/2, and then your partial with respect to whatever is here of your inside, which is either 2x, 2y, or 2z in each case. And then the 2's cancel, so what you end up with is xy and the sum of squares to the 3/2. And the reason that you have the minus is your minus half power. When you bring it down in front, you still have the minus sign. So what happens then is you get 6 of these results that look like this, and I have them here where I've taken this out as a common factor. And then you can look at your vectors with the products, and this one and this one are the same thing. So you have yz minus yz, xz minus xz, and xy minus xy. So you do get 0. Well, what we'll do tomorrow then is back to these 2 Green's theorems, the circulation curl and the flux divergence. And what the problems consist of is some examples where for a given path they want you to work the line integrals separately and see that they are the same thing. In other words, for circulation curl type, they want you to do a line integral around the closed path, the circulation, and then see that if you take the k component of the curl, which is this difference here, and integrate that over the region that the path encloses, that you get the same thing. And they have some problems that are circulation curl and some that are the flux divergence, where you'd do the line integral that is like this, which would be your flux integral, and then you'd do the integral over the enclosed region as a double integral like that, and see that you do get the same numbers. So that's essentially what we'll do tomorrow, that kind of thing. So we're getting there. So I'll see